Okay, continuing our discussion on complex numbers and imaginary numbers, we have now found out what they are, why they pop up, and more importantly, how to get our calculator to stop calling them errors, because that's pretty rude. They're not errors, they also have feelings. So, now what we want to talk about is how to manipulate them. How do you add a complex number to a complex number? How do you add an imaginary number to an imaginary number? Yeah? Right, I'm going to start with two complex numbers. Keeping it nice and simple, 1 plus 2i and 4 plus 6i. Remember, these are both complex because they have a real part, the 1 and the 4, and an imaginary part, a 2i and a 6i. Okay? Just a brief caveat again, the 2i is not, well, it is a real number times an imaginary number, but because they are multiplied together, it makes an imaginary number. Okay? So, on its own, this is not a complex number, even though it's got a real and an imaginary part. They have to be added or subtracted from one another. Yeah, do that. I keep losing this rubber. Don't tether to me. So, I've got these two. And the question is, how do I add them together? How do I multiply them together? How do I divide them? How do I subtract them, etc., etc., etc.? Well, it's very simple. You pretend it's normal algebra. Because it is. Granted, it's in a complex space, but it is basically real algebra. What do I mean by that? Just pretend the I is an X. If I is too scary, it's an X. You've used an X before. If I add them together, I can add like terms. So my real numbers can add together. 1 plus 4 is 5. And my imaginary terms can add together. 2i plus 6i, ASI. Nothing scary. It's just normal algebra. Pretend there's an X. Add the like terms, things that have i's and things that don't, and go from there. Okay? Exactly the same thing happens when we multiply. But when we multiply, strange things happen. Let me show you what I mean. So let's say I multiply these two together. Well, we're going to multiply them the same way we would normal algebra with x's, as I said. So every term is multiplied by every term. You can use FOIL or whatever method you wish to multiply two brackets. So let's just do it normally. So we'll have 1 times 1, or sorry, 1 times 4, 4. 2i times 4, again, imagine it was 2x times 4. That's 8x, this is just 8i. Then we'll have 1 times 6i. And then we'll have 2i times 6i. And again, if it was an x, you know it would just be 12x squared. So it's 12i squared. Okay? I can collect like terms and I can get 4 plus 14i plus 12i squared. Now, if this was an x, this would be the maximum we could get to. But it's not. Okay? It's not an x. It's an I. Why are they different? Well, one comes first in the alphabet. Why else are they different? Because I actually has a value. Remember, when we're using x in an algebraic expression, it's because we don't know what x is. It could be anything. It could be 3, it could be 15, it could be 4.76413. We don't know what it is. But we definitely know what I is. It's the square root of minus 1. So I could technically replace this equation as 4 plus 14 root minus 1 plus 12 root minus 1 root minus 1. Now, it'd be a bit silly to do that here because 14 root minus 1 is just a bit messy. It's absurd. But it is useful when we have an I squared. Because if it's I squared, that's the square root of minus 1 times the square root of minus 1. Well, we know that if I have root anything times root anything, I'm basically just cancelling out the square root, right? It's essentially saying minus 1 square rooted squared. They cancel and I'm just left with minus 1. So it's actually quite interesting. My I squared, which has mysteriously disappeared from there, definitely not because I made a mistake and I've had to edit this and go back and it doesn't matter. My I squared has become real. And specifically, it has become minus 1. And it will always, always, always be minus 1. Whenever we see an I squared, we should be thinking, that's minus 1. So here, my 12i squared becomes 12 times minus 1 minus 12. And this whole thing simplifies even further into 4 minus 12 is minus 8 plus 14i. This is very, very important. I squareds become minus 1s simply because of the way that they work. Yeah? We can keep going with this. We could also say I cubed. Well, I cubed, if that ever came up, is root minus 1 times root minus 1 times root minus 1. Well, root minus 1 times root minus 1 is root minus 1 squared, which is minus 1, times root minus 1, well, that's I, so I have minus I. I cubed is minus I. What about I to the 4? Well, I to the 4, simplify things, is I cubed times I, so it's minus I times I. Well, minus I times I is minus root 1 times root 1. Well, we know that root minus 1 times root minus 1 is minus 1. Times by minus 1 is 1. So, these are 4 very, very important results. I have I squared, which is minus 1. I have I cubed, which is minus I. And then I have I to the 4, which is 1. This is a repeating pattern that is very, very, very important. Why do I keep losing this? It is very, very important. And it's something that we need to remember because we are going to see a lot of I squareds, I cubeds, I to the 4s, I to the 7s, I's, etc., etc. So, I've got I squared, I cubed, I to the 4, I to the 5, I to the 6, and I'm just going to show you we've got a repeating pattern. I squared is minus 1, obviously I is just I cubed is minus I, and I to the 4 is 1. After this it repeats, because I to the 5 is I to the 4 times by I is 1 times I is I, and we just keep going. Minus 1, minus I, 1. I minus 1 minus I, 1. I minus 1 minus I, 1. We can use this quite well. Every fourth value it repeats. Okay, it is a periodic sequence of the period of 4. So I can use this to say, well, you know, if I wanted to find what I to the 50 was, well, I would have to write it out in terms of what are the closest, let me try that again. We'd have to try and think, what are the closest multiples of 4 to 50? That would usually be the way to do it. So I'd have I to the 48, I to the 49, I to the 50, I to the 51, and I to the 52. And we would map it, okay? This is how I would do it. My first I to the 4 is 1, so every I to the 4 is 1. So I to the 4, I to the 8, I to the 12, I to the 48 are all equal to 1. I to the 52 is also going to be equal to 1. And then we can fill in the rest. I minus 1 minus I, 1. This is how I work with sequences with periods. Yeah? So I can then say that I to the 50 is minus 1 without having to calculate anything myself. Now, obviously, if you're in an A-level exam, you have a calculator, it will do all this for you as long as it is in I mode, right? You need to make sure it's put into complex mode so it knows what it's doing. But if it does, you're fine. But if you're in step or, you know, you just like to punish yourself and not use a calculator, just remember it is a periodic sequence. Right. The last thing we want to talk about is something that sounds very, very scary, but it's not. It is called complex conjugation. Okay? Complex. So complex meaning, you know, real and an imaginary number. Conjugation. Now, this is actually a very, very important concept in physics and maths, especially if you look at some quantum operators. There's some complex conjugation going on in there, hidden away. But in terms of words you will understand, conjugation is very, very simple. We take a complex number, 1 plus root 2i, for example. This is my complex number I will denote with a z. From now on, our complex numbers are going to be z's. In order to conjugate this, well, all I need to do is flip the sign on my imaginary part. So my imaginary part is plus root 2. So my conjugation turns it into minus root 2. And we write a complex conjugate with a little asterisk star there. So I've got 1 plus root 2i is z, 1 minus root 2i is my complex conjugate. If it was 1 minus root 3i, if that was my z, my complex conjugate would be 1 plus root 3i. Right, why is this important? Well, this is important because a complex number has a very, very special property. That property is that if I take a complex conjugate and I multiply it by its complex value, I get something very special. So let's do that here. Let's do 1 minus root 3i times by 1 plus root 3i. And see what we get. So 1 times 1 is 1. Minus root 3i times 1 is minus root 3i. Root 3i times 1 is plus root 3i. And then I've got minus root 3 plus I plus root 3i times plus root 3i. Blech, can't speak. Minus root 3i times root 3i. So I have minus root 3 times root 3. Well, that's minus 3. And then I times I, which is I squared. Now, what do we know about I squared? It's minus 1. So this actually becomes plus 3. And here, I've got minus root 3i plus root 3i. They cancel. And I just get 4. Whenever you multiply a complex number by its conjugate, you get a real number. Specifically, you get, for a complex number a plus bi, z times z star is a squared plus b squared. You are turning it into a real number. And this can be very, very important, as we will shortly see.